Okay, here's an example problem of how to use free body diagrams and summing up the forces in order to find a solution to a problem. A ball is rolling at 6 meters per second and takes 6 meters to come to a stop as it rolls across the floor. What is the coefficient of friction between the ball and the floor? So I've got a little picture of a ball, and I'm going to assume it goes from left to right, and I'll start with a free body diagram. So I'm going to go through my list of questions while I do the free body diagram. I'll start with, is it on a planet? Well, yeah, we're going to assume it's on the Earth. So that means I'm going to have the weight. That's going to be my first arrow going down. I'm not going to label it as W. I'm going to label it as mg. Just going to make my life a little bit easier to start thinking about not W, but mg for the weight. Is there a contact surface? Well, yep, it's rolling on the ground. So that means I'm going to have a normal force. Doesn't say anything about friction, just normal force. So there it is, there's my normal force, and it's going to go perpendicular to the surface. That's the definition of normal, perpendicular. So it's going to go upwards. And the ball is not jumping off the ground, and it's not plummeting down through the ground. So the two forces are equal. So I'm making the same length here. Is there surface friction? Yes, it asks for the coefficient of friction. So that's definitely surface friction. So that exists. Friction is parallel to the surface of contact and opposite the direction of motion. So parallel means horizontal, opposite the motion, it's going to go from right to left. And I'm going to use a cursive F to indicate friction. Okay, our next set of questions that we know, is there a rope? Nope. So are there other forces involved? No. Great. Is it changing velocity? Yes, it's going from 6 meters per second to a stop. So since it's changing velocity, there's a net force acting on the ball. And the net force, in this case, it's got to go the same direction as friction because there's no other force on the diagram. So MA net has got to equal the friction. So there's our net force. There's our free body diagram. Now let's switch gears and do what we've done in the past and list our givens. We know the initial velocity is 6, final velocity is 0 because it comes to a rest. The distance is 6 meters, and I'm looking for the coefficient of friction. Wow, I haven't even really addressed the question so much yet. Now let's think about the question and come up with a strategy. So I want to find the coefficient of friction. So I only know one way to find the coefficient of friction at this point, and that's going to be with our fun equation. F is equal to mu times eta. That's great. So I'm looking for mu, but I don't know F and I don't know eta. Well, eta, okay, if I want to find it for this equation, I can find it from a free body diagram because eta minus mg will equal 0. It's all the vertical forces in this case. Well, that's great. That's half the answer. Now I got to find friction. The only other way I can find friction is by using another free body diagram, using the horizontal givens, because that's the direction of the friction force. And if I do that, I'm looking at the picture and I'm seeing MA and I'm seeing friction, but I don't have A anywhere. But I can find A using kinematics. So now at this point, looking at the free body diagram and my givens, I can find everything. But I'm not going to do all the work in this order. I'm going to switch it up from bottom to top. So really, this is the order I'm going to do. Kinematics, friction, normal force, and then mu. We'll get to our answer. So let's start with the acceleration. I'm going to find the acceleration from kinematics. So if I look at my givens, I can use v squared equals v naught squared plus 2ax. Isolate a, v squared minus v naught squared divided by 2x. And then a is equal to, well, negative 6 meters per second squared minus 2 times 6. That's going to be negative 3 meters per second squared. Negative, well, okay, that makes sense because it's slowing down. So according to kinematics, that makes sense. But now I'm going to switch gears. I'm going to use that A into my formula for free body diagrams. So when I'm summing up the forces in my free body diagrams, I'm going to sum up the forces in the x direction. So that's going to give me MA divided by, MA is equal to friction because MA is the answer. It's the only one going left, and friction goes the same direction. So I'm going to say going left is positive in this example, just to make the math easy. I could make it negative and make MA negative and friction negative. It'll work out the same. But now that I'm switching gears away from kinematics into my free body diagrams, where my direction tells me my signs, the sign on A is no longer negative when I'm doing the free body diagrams. The sign on A is going to be positive, and then I'm going to let my free body diagram logic dictate what the sign's going to be from here on out. So I'm going to leave that as a 3 in this case. All right. So I'm all set here. And now I can make a quick substitution on my friction, and this is pretty typical. Nice thing about friction is the one force that can tie the vertical and the horizontal equations. because the normal force is vertical and friction is horizontal, and I do that with this substitution of mu times eta. So ma is equal to mu times eta. Now I'm not really doing a whole lot here. I'm just kind of solving some of the problems and trying to simplify and isolate. I know that I want mu, and that's kind of why I did the mu times eta thing, because I wanted to get some the mu in there somewhere. I'll isolate mu, so mu is equal to ma over eta. I'm not sure that helped me. Oh wait, eta is in the free body diagram for the vertical forces. So if I sum up the forces in the y direction, it's equal to 0 because it's not accelerating in the y direction, only horizontal. That's equal to eta minus mg. So eta is equal to mg. And that came from the fact that 0 is equal to eta minus mg. And then I moved it around a little bit. It's a little out of order, but we'll go with it for now. So mu is equal to ma divided by mg. So all I'm doing here is taking what it says for eta is equal to mg, and just subbing it in. Wow, there's a whole lot of substitution going on here. So mu is equal to ma divided by mg. Wait, this is the same object and the same mass. Cool. Masses go away. So now all this work has led down to this simple little equation. Mu is equal to the acceleration divided by g. So mu is equal to, notice it's a positive acceleration. Remember, once I get away from the kinematics and get into the free body stuff, I'm going to let my free body logic tell me anything about the signs that I need to do. That's when I'm adding and subtracting them in those summations. So positive 3 meters per second squared divided by positive 9.8 meters per second squared, and that gives me the coefficient of friction. So the coefficient of friction is 0.306. No units, it's just the percentage of the normal force. So about 31% of the normal force goes into friction.